Welcome to our presentation on contrastive learning with frequency domain interest trends for sequential recommendations. This innovative approach redefines sequential recommendation systems to better capture user interest trends, both gradual and sudden. We are excited to share this work with you today. Sequential recommendation systems are designed to predict a user's next interaction based on previous behaviors. However, a current method such as CNN, RNN, and transformers often fall short when it comes to adapting to fast-changing user interest or handling noisy data. These methods focus mostly on low-frequency patterns, which means they struggle with abrupt shifts in preferences. To solve this issue, uh, developers developed CFIT for SREC. This model operates in the frequency domain and uses contrastive learning along with augmentative frequency domain samples to better capture both gradual and rapid changes in user behavior. Moving to the next slide. Contrastive learning is a powerful method for generating high-quality self-supervised representations. It works by making positive pairs, which are related sequences, more similar while making negative pairs, which are unrelated sequences, which are less similar. CFIT for SREC applies this idea in a unique way by operating in the frequency domain. This enhances the model's ability to handle noisy and sparse data, which are common challenges in real-world applications. Moving to the next slide. The Fourier transform plays a critical role in CFIT for SREC. It takes user interaction sequences from the time domain and transforms them into the frequency domain. In this new representation, low frequency components represent gradual trends in user interest, while high frequency components capture sudden shifts or spikes in preferences. By using this transformation, the model can analyze user behavior more effectively, overcoming the limitations of traditional time domain approaches. Moving to the next slide. CFIT for SREC incorporates three levels of frequency-based augmentation. Low-pass augmentation focuses on smooth long-term trends by filtering out noise. High-pass augmentation emphasizes rapid short-term changes in preferences. Finally, band-stop augmentation randomly removes specific frequency components, which prevents overfitting and enhances generalization. This augmentation generates a diverse set of training samples, making the model more robust overall. Moving to the next slide.
First part of the model flow is the data representation. So the first step involves collecting user interaction sequences as time domain data. Now these sequences represent a user's historical interactions with items like the products, movies, or the services. For example, a user might interact with items in the order like item B, then item C, then item D. And these sequences show how the user preference evolve over time. These sequences form the core input to the model, capturing user behavior over a time window. However, relying solely on the time domain data can limit the model's ability to identify sudden shifts in preferences, which may be due to the noise or the sparse interactions. So to overcome this, we move on to the next embedding layer. So to process this raw interaction data, the model employs an embedding layer that maps each item to a d-dimensional vector. Now each vector represents the item's attributes in a format that model can process. For example, item A could be mapped to a certain vector, say let us suppose minus 0.34, 0.7, and so on. Additionally, positional encoding is also employed to preserve the order of the interactions. For example, this step ensures that the model can differentiate between different orders like A, B, C, as well as C, B, A, as the order reflects distinct user behaviors. So the output of this layer is a sequence of meaningful item representations that serve as an input for further processing. So as a part of the further processing, we move on to the transforming sequences to frequency domain. So what is a core innovation of the CFIT for SREC is that it converts the data to the frequency domain. So this step separates the sequences into low frequency components, which captures smooth long-term behavioral trends. Now the high frequency components, which reflect abrupt short-term shifts in preferences, are also covered by this. So by working in the frequency domain, Model can analyze user behavior more effectively, distinguishing between stable interests, example consistently like romantic comedies, and then causing a sudden spike in like watching a trending horror movie. So this transformation helps the model overcome limitations of the time domain data, such as noise or the fast changing preferences. So now, next we move on to the data augmentation part of the model flow. So to further enhance learning of the CFIT 4S rec, it applies frequency domain augmentations, creating diverse variations in the input data. Now, these augmentation emphasize different aspects of user behavior, like the low pass augmentation. So this filters out the high frequency noise to focus on the gradual long-term interest trends. Further, the high pass augmentation highlights sudden fast evolving preferences by emphasizing on the high frequency components. And the last one is the band stop augmentation, which randomly removes certain frequency components to introduce variability, forcing the model to generalize better and avoid overfitting. So basically, these augmentations create multiple versions of the user interaction sequences, enabling the model to learn more robust representation of the user preferences. So next comes the multitask learning. So basically, contrastive learning is a self-supervised approach integrated into CFIT for SREC to refine its understanding of user behavior. Now, the model compares the positive pairs and the negative pairs. So, what are the positive pairs? Positive pairs means the different augmented views of same sequence. Example, original low-pass versions of a user interactions. And while the negative pairs means sequence from the unrelated users representing the dissimilar behaviors. So the model is trained to maximize the similarity score of the positive pairs as well as ensuring consistent learning of a user's preferences. And as well as along with that to minimize the similarity score between the negative pairs, distinguishing one user's behavior from the others. For example, if a user A prefers action movies, let us suppose, and user B prefers romantic comedies. So the model learns to separate these preferences even if they occasionally overlap due to noise. So this helps strengthen the model's ability to capture nuanced behavior patterns, making it robust to noisy and sparse data. And then next we move on to the recommendation learning part. So in parallel with the contrastive learning, our model performs a traditional recommendation task, predicting the next items in a user sequence. And the model combines the user's learned representation from the contrastive task with the sequence to predict the most probable next interaction. The softmax layer calculates the probability of all items, recommending the one with the highest likelihood. For example, if a user interacted with the action movie 1, then 2, and the thriller movie 1, the model might recommend action movie 3, reflecting both gradual and sudden preference shifts. So by integrating the contrastive recommendation learning, the model ensures adaptability and accuracy in real world scenarios. Now, next is the multitask learning. So CFIT for SREC employs a multitask learning ability to balance the two key objectives, that is a contrastive loss and second one is the recommendation loss. So basically, what is a contrastive loss? These loss helps the model to learn distinct patterns of user behavior by comparing the positive and the negative pairs. It strengthens the model's ability to handle noisy and sparse data by emphasizing consistency in the user's augmented views. Now, next part which it balances is the recommendation loss. So basically, this loss focuses on accurately predicting the next item. It uses binary cross entropy loss function to ensure the model rank items correctly in a user preference. So by combining these two losses, the model achieves the generalization. The contrastive loss improves the model's robustness, enabling it to handle varied user behavior and evolving preferences, while the recommendation loss causes precise predictions for the next user interaction. So basically, this dual objective of training makes a model more adaptable to real world scenarios where user preferences are dynamic and data quality varies. And the final part is the making prediction in real time. Once the model is trained, it is deployed for real time recommendation. Here's how the inference process works. Like first, if the input is given, like a new user interaction sequence is fed into the model. For instance, a user might have interacted with the items, say item 5, 7, and 9. Then the processing takes place where the transform-based encoder processes the sequence by applying learned frequency domain augmentations to analyze both gradual as well as the sudden interest trends. Now, leveraging the representation learned through contrastive as well as the recommendation learning, a prediction is made. So using the combined insights, the model predicts the next likelihood interaction. For example, based on the provided sequence, the model might recommend item 12, aligning with the user's evolving preferences. And this real-time capability allows a model to dynamically adapt to users' behavior, making precise and context recommendations, as well as even handles the preferences shifted rapidly. So yeah, next move on to the Priyanshu to explain the experimentation part.
So now I'll explain the experimental setup we used for this model. We tested CFIT4S Rec on several well-known datasets, including Amazon Beauty and Baby, and the Microsoft News dataset and Movie Lens dataset. To evaluate performance, we use metrics like hit rate, which measures how often the model predicts correctly, the NDCG, which considers the accuracy of ranking predictions. These diverse datasets ensures a comprehensive assessment of a model's capabilities. Moving on to the next slide, performance comparison. CFIT4S Rec outperformed state-of-the-art models like DuoRec and CL4S Rec. For instance, it achieved a 24.75% improvement in HR5 on the ML 1 million dataset. Additionally, it showed superior robustness against challenges like sparse and noisy data. The performance gains are illustrated through detailed charts and comparisons, which clearly demonstrate the advantage of our approach. Next, moving on to the next slide, noise ratio analysis. CFIT4S Rec demonstrated exceptional performance even in challenging conditions. In scenarios with limited training data, the model maintained high accuracy. Similarly, when noisy interaction were introduced, CFIT4S Rec outperformed other models by a significant margin. Graphs and data highlight its consistent performance across varying levels of data sparsity and noise. Now, moving on to the final conclusion, CFIT4S Rec redefines sequential recommendation system by introducing frequency domain analysis and robust contrastive learning. The innovative use of augmentation allow it to capture diverse user behavior effectively. Extensive experiment confirm its superior accuracy and adaptability, setting a new benchmark in the field of recommendation system. Thank you.